Rotating cylindrical shell. A cylindrical shell with radius capital R and length W carries a uniform charge Q and rotates about its axis with angular speed omega. The center of the cylinder lies at the origin and its axis is incident with the x-axis, as shown in figure. Part A, what is the charge density sigma? The charge density sigma, the surface charge density sigma, is the total charge stored on the shell divided by the surface area of the shell. So what is the surface area of this shell? The surface area for a cylindrical surface, A, is equal to the circumference 2 pi r, capital R, multiplied by the length, which is W. So you can see from the figure, it is 2 pi r, the circumference, multiplied by W. That gives us the surface area. So we can see that the charge density sigma is equal to Q, the charge it carries, divided by 2 pi capital R W. That is the charge density. Okay, let's look at part B. What is the differential current dI on a circular strip of the cylinder centered at x and width dx? So this is basically the strip. So we're asking the current carried by this strip. Okay, so in part B, what is the area of the strip? So let's start with the area. The area of the strip is the circumference 2 pi r multiplied by its length, so it is 2 pi r dx. So you can see here it is 2 pi r multiplied by dx. That's the surface area of this strip. So that we can calculate the charge it carries. dq is equal to sigma times its area dA. Now sigma we found in part A, capital Q divided by 2 pi capital R W multiplied by dA, which is 2 pi R dx. So 2 pi r's will cancel out and I will be left with Q dx over W for the charge. So I will see that the charge it carries is Q dx divided by W. The angular speed of this cylindrical shell is 2 pi, the angle we traverse in one period, 2 pi divided by the period. So t, the period, is equal to 2 pi divided by its angular speed, omega. So what is the current this strip carries? It carries a charge dq in one period. So in one period, one full revolution, it carries this total charge dq that we calculated as q dx over w. So it is q dx divided by w multiplied by omega divided by 2 pi, 1 over the period, omega divided by 2 pi. So this gives us q omega dx divided by 2 pi w let's rewrite this answer. The current carried by this strip, dI, is equal to q angular speed omega dx divided by 2 pi w. So that's the answer to part B. Part C, use the magnetic field on axis of a circular current carrying loop. Mu 0 I a square over 2 parentheses x square plus a square to 3 halves. A is the loop radius, I is the current. So we're going to use this result to write an expression for the differential magnetic field dB at the origin due to this strip. Okay, so let's copy this answer. The magnetic field due to a circular current loop is mu 0 I a square, where a is the loop radius, 2 x square plus a square to the power 3 over 2. So here, if I apply this to this problem, a is capital R, and the current is dI, the current carried by this strip. Therefore, I can write dBx as mu 0 dI r squared divided by 2 x squared plus capital R squared to the power 3 over 2. And I know what dI is, so dBx becomes mu 0 capital R squared q omega angular speed dx divided by 4 pi capital omega, or w, x square plus capital R square to the power 3 over 2. And I can find its direction. So let's follow this current with our right hand, 4 fingers. If you curl your fingers, 4 fingers, in the direction of the current, then you will see that the magnetic field is in I-hat direction. That's the direction defined by our thumb. So we can find the direction as well. So using our right hand rule, dBx vector is mu 0 q omega capital R square dx divided by 4 pi w x square plus capital R square to the power 3 over 2, and it is in I-hat direction, the direction we have found using the right hand rule. And in part D, integrate to determine the magnetic field at the origin. So finally, we will find the magnetic field at the origin. Bx is integral dBx, because all such strips will produce a magnetic field in the same direction. So if I go from 0 to w over 2 and minus w over 2 to 0, the answers will be identical. So I might as well say this is twice the integral from 0 to w over 2 dBx. And that is equal to mu 0 q omega r squared divided by 2 pi w. Because of this 2 here, this 4 will cancel. And I will have inside the integral from 0 to w over 2 dx divided by x squared plus capital R squared parentheses to the power 3 over 2 I hat, that is at the origin. Okay, so what I'm going to do to perform this integration is to let x is equal to capital R tangent theta, so that dx is equal to capital R secant square theta d theta, and you can see in this right triangle tangent theta is x divided by capital R. So this integral dx over x squared plus capital R squared to the power 3 over 2 is capital R secant square theta d theta, that's dx, divided by capital R square tangent square theta plus capital R square to the power 3 over 2, and that integral is capital R secant square theta d theta divided by capital R cube parentheses 1 plus tangent square theta to the power 3 over 2. So this becomes, because we have a cancellation here, this is R square, 1 over capital R square integral secant square theta divided by, because 1 plus tangent square theta is secant square theta, secant cube theta at the bottom. So this is 1 over capital R square integral of 1 over secant theta, which is cosine theta d theta. Okay, the integral of the cosine is sine, so we will have 1 over capital R squared sine theta as the answer, which is 1 over capital R squared. What is sine theta from this right triangle? I can see it's x divided by square root of R squared plus x squared. So this is x divided by x squared plus R squared square root. So the integral from 0 to w over 2 dx divided by x squared plus R squared to the power 3 over 2 is actually equal to 1 over R squared x divided by square root of x squared plus R squared evaluated between 0 and w over 2. I'm now ready to write the magnetic field. Bx is mu 0 q omega divided by 2 pi w. So this is where I started. Here, mu 0 q omega over 2 pi w. There was an r square, but that r square cancels with this r square. So it's just this one. Then I evaluated this at x equals omega over w over 2. So w over 2 divided by w square over 4 plus r square square root and minus 0 in I hat direction. So this is just putting the limits of integration. And finally, I find the magnetic field Bx to be mu 0 q omega divided by, these w's will cancel, divided by two pi square root of w square plus 4r square in I hat direction. So how did that happen? W square plus 4r square over 4 square root, that gives me 1/2. It goes upstairs, that cancels with these 2's, and I'm left with a 2 pi here. So this gives me the final answer for the magnetic field at the origin. Okay, so in this problem, first we started out by writing the surface charge density, capital Q, divided by the surface area, which is 2 pi r times W. Then we wrote the area of a strip, which is 2 pi r times dx, that's the area. The charge is basically dq, that's sigma times dA, so q over 2 pi r w times 2 pi r dx. And this charge, the charge stored on this strip, is basically making one full turn in one period. So dq divided by the period is the current, but the angular speed is 2 pi divided by the period, so period is 2 pi over w. I substitute that result to find di, the current carried by this strip, q omega dx over 2 pi w. And what is the magnetic field due to this strip? But well, here I use the result for the magnetic field on axis of a circular current carrying loop, where I notice that the loop radius is capital R and the current I'm talking about is di. So with that, and also using the right hand rule, 4 fingers of the right hand curl in the direction of the current, the thumb points in I hat direction, I find the magnetic field, and I integrate it from 0 to w over 2 and multiply it by 2 because there's a contribution from this side, and from 0 to w over 2 and minus w over 2 to 0. I will get the same answer due to symmetry, so it's just multiplied by 2. I perform this integration with a change of variables, and finally I get my answer in I hat direction, mu 0 q omega over 2 pi w square plus 4r square square root.